So, as was mentioned in the last video, a battery is a voltaic cell, and we know that batteries have voltages assigned to them. So how do we figure out what the voltage is going to be for a battery or for any electrochemical cell? Well, we have to figure out some potentials for the half reactions that are taking place. So the voltage potential that we measure is a relative scale, and it's measured relative to something called the standard hydrogen electrode. So what we say is that if I am reducing hydrogen ions to hydrogen gas, so in this half cell I have reduction of H plus in solution. I'm forming bubbles of hydrogen gas because the H plus is being reduced to H2 gas. Now you notice in this setup it's a little bit different. This is the electrode. You know, it's platinum electrode because you can't really have an electrode of H2 itself because H2 is a gas. So whenever we have things that are not metals that we want to either oxidize or reduce, we use a platinum electrode, which is inert, but it provides the surface for electron transfer. Okay. So now we have this standard hydrogen electrode, and we compare everything else to it. So the standard hydrogen electrode is assigned the 0 point. So things can either have a higher voltage than a hydrogen electrode, standard hydrogen electrode, or lower voltage. So, for example, if we want to know the voltage for the copper half reaction, we hook up a voltaic cell, and we have copper being reduced. And in this case, the hydrogen is being oxidized to H+, but we call that 0. And so when we measure the voltage, we notice we get 0.340 volts. So the potential of this half reaction where I have Cu2 plus 2 electrons yielding Cu, I'm going to call that voltage 0.340. Okay, and that's a standard potential, so this is carried out under standard conditions. Standard conditions, remember, same as thermodynamics, 25 degrees Celsius, 1 atmosphere pressure, and since we're dealing with solutions, we're dealing with 1 molar solutions. Okay. So we would say the standard potential, which is E cell, is cell potential. Standard cell potential, remember degree sign means standard potential, potential measured under standard conditions. So the standard cell potential for this half reaction is 0.340 volts. Okay. So what we end up with is a table of standard reduction potentials in aqueous solution. So you have this as one of your handouts. This is just a copy of the top part of that potential table. So F2 gas being reduced to F2 ions, the standard cell potential for that half reaction is 2.87. Now what you'll notice about this table is everything is written in terms of reduction. So when we go to calculate standard voltage or standard cell potential from this table, we're going to have to keep in mind that all the values listed in this column are for reductions. But remember, in a galvanic or voltaic cell, we have both oxidation and reduction. So we'll need to keep that in mind when we go to do our calculations. Okay. So if I want to calculate the cell potential for a galvanic cell based on this reaction, the first thing I want to do is to split this up into its 2 half reactions. So I know I have aluminum plus 3 electrons is becoming aluminum metal, because aluminum 3 plus, I have to add 3 electrons. So then I know my magnesium is becoming Mg2 plus 2 electrons. Okay. So I want to figure out the balanced chemical reaction because you notice this is not balanced as written, and I want to calculate E cell. So to give the balanced reaction, Here are my two half reactions, number of electrons that are in there. I have to multiply this by 2, and I have to multiply this by 3. So that tells me that 2Al3 plus 3Mg yields 2Al plus 3Mg2 plus. Okay, so now this is balanced. Now I'm going to go to my standard reduction potential table to find out the voltages for each of these half reactions. So when you look up the half reaction for aluminum, you notice this is reduction. So when you go to the table, you'll be able to find this half reaction as written. The voltage that goes with that half reaction is negative 1.66 volts. Okay, then I want to get the cell potential for this half reaction. But you'll notice this is an oxidation half reaction. So it's magnesium yields magnesium 2 plus 2E minus. So on my reduction table, I have to look for the reverse reaction. So on my reduction potential table, I'm looking for Mg2 plus 2E minus yields Mg. When you find that one, you find out that magnesium, as listed as reduction, so on the table, magnesium is listed like this. On the table, the voltage is negative 2.37 volts. However, I'm not running this reaction, I'm running the reverse reaction. So since I'm running the reverse reaction, what I'm going to do is flip the sign. So if the reduction potential is negative 2.37 volts, the oxidation potential is positive 2.37 volts. And then the next thing to note is that with cell potentials, even though to balance this chemical reaction, I had to multiply by 2 and multiply by 3, I do not multiply voltages by this 2 or this 3, because voltage is an intensive property, which means it's independent of the amount of stuff we have. It is not extensive like delta H. Delta H is extensive. It changes depending on how much we have. This is intensive. It doesn't change depending on how much we have. So if I want to know the voltage for this, I just take those two and add them together, and when I do that, I get 0.71 volts, and it's a positive 0.71 volts. So if I have a galvanic cell, this is telling me I have a galvanic cell. A galvanic cell is a spontaneous reaction. It is thermodynamically favored. So in order to have a galvanic cell, I need a cell potential that is positive, because a positive cell potential, a positive E cell, and this would be standard because it's from the table, a positive E cell means that reaction is thermodynamically favored. So positive, thermodynamically favored, it's a galvanic cell. If I get a negative voltage, that means that you cannot make a galvanic cell from that combination of reactions.